Good morning. Um, so I want to mention something first. So in your project, I saw some of you want to do some force analysis, but so far in the kinematics, we haven't mentioned anything about force. And because usually when we consider the force, we need to consider the mass. But in this course, we never consider the mass of a mechanism. So that's why we never consider the force. But actually, if you would like to consider force, we have another aspect to consider the force. So I use these two examples to, if you would like to analyze the force, well, there's actually something we can do in a very simple way. So usually, when we take this one as example, we sometimes use this one and maybe to convert the motion. So let's say the omega 2 is the input, and omega 4 is the output. Or another case, if we use this one as the input, and this one as the output. If I use this one or this one as input, I may install a motor here or here. And you may want to use, if you use this crank slider, you may use this slider to push something. And so you may want to know how large the force can be for this slider. So if you are using this slider to push something, that means you need to apply certain force on an object. But how do I know how? So in order to provide this force, you need to know how much torque you need to, this motor need to provide for this mechanism to generate this force. And how can I obtain this force? If I want this mechanism to output certain force, then I need to find T2 here. T2 means the torque from the actuator, from the motor. And how can I know how much torque I need to apply in order to achieve certain force? Actually, if we already know the velocity, then we can get this immediately. How? For mechanism or for system, we usually say the energy is conservative. So it means the input energy should be the same as the output energy. Because the energy cannot just disappear, or it will still disappear because sometimes there may be some friction inside. So the input energy will be the output energy plus the, what should I say, the energy if there is friction within this mechanism, then the friction will consume some energy. But if we assume there's no friction, let me remove this one for now. If there's no friction within this mechanism, then there should be no energy loss from input to the output. So I said the input energy should be the same as the output energy. Right? Then what's the input energy? Or if I do the time derivative for this one, because later on I'll start with this one. So what's the input energy? The input energy is Right now, because the input is torque, so I will use torque, T2. Then the energy is the force times the displacement. So for this one, right now, I'm applying the torque on this bar, this link 2. So the displacement is theta 2, or delta theta 2. Depends on how much you move the input link. How about the output energy? Right now, it's applying certain force to an object. So right now, the force, well, it's just the F. We call it F4 because it's on link 4. And times the displacement. Let's say the displacement is x. So if there's no energy loss, I can have this equation. Also put a delta here. The input energy should be the same as the output energy. Any questions so far? So right now I have this T2 delta theta 2 equals F4 delta x delta x. Yeah. It's not quite convenient to use this equation. So instead of using this equation, I do a time derivative for this equation. Then you will get T2 omega 2 equals F4 x dot. So just do a time derivative for this equation and you will become this new equation. And once we finish the velocity analysis, we can get this too, right? We will know the velocity of link 4 and know the, this one is the input. We will provide the omega 2 for this mechanism. So we know this too. So once we know the velocity, rotational velocity and this linear velocity, we can immediately get the ratio between T2 and F4. So let's say if I need 100 Newton, then you can immediately get how much you need to provide for T2. Yeah, so if you have a desired force for the output, you can just based on this equation, once you finish the velocity analysis, you can immediately get the T2, the required torque for the motor to drive this mechanism and to provide this force. Yeah. We simply use the relationship between the velocity and we can get the relationship between the force and torque, the input and the output. So if you would like to perform some force analysis, yeah, you can simply use this one to find the force from the input and force from the output, just based on the velocity analysis. So that's in case you want to perform some force analysis, you can use this method. Any question for this one? So if it's this case, so this case I use omega 2 as the input, omega 4 as the output. And let's say I apply the T2 here, then here I will get T4. Then you can get a similar equation, T2 omega 2 equals T4 omega 4. Any questions? Okay, then we'll go back to the cam design. Okay, so I'll erase this. Okay, so last time we talked about the uniform motion. So right now what we are doing is, suppose we want this cam follower system, and we know the desired displacement. We know a desire we want. Let me change. So last time we are saying if we want a motion fit certain requirement. Right now the requirement is from this point to this point. The displacement will rise from the bottom to the top. So we need a certain curve to connect these 2 points. Yeah. Our requirement is to rise from this point to this point within this period. So there are several options. You can use a curve. You can use any different type of curve to achieve this. Yeah. And last time we used a straight line to connect these 2 dots. But we found it's not a very good option because so for displacement, it looks okay, but for velocity, you will see the velocity will suddenly change at this point. It will change from 0 to a certain value at this moment. And so if we have velocity looks in this way, which is not continuous, then you do a time derivative for this one, you will get infinite acceleration. And this is not good. And also if you get infinite acceleration, you also get infinite jerk. So we know this one is not a good way to design the displacement for the follower. So we may need to use other curves instead of this one. And just a quick review. So last time we do the curve for the rising part. We haven't done for the fallen part, so I'm going to do the fallen part first. Although this one is not good, but we'll still do that first. So you'll get an idea how to connect from the top to the bottom. So for rising part, it's very simple. For rising part, this one. For rising part, the curve is basically it's a straight line. So right now, theta is the x-coordinate and s is the y-coordinate. Yeah, there's a displacement for this graph. Right now I'm writing, I try to describe this line. So I use basically this line can be described as a slope times theta. But right now, if I write in this way, I'm considering theta start from this point. So from 0 to beta. If I set this one as theta equals 0, then I can write the equation for this straight line in this way. And you will reach L. You reach L when theta equals beta. And this curve only valid for theta larger than 0 and smaller than beta. So this one is a curve for the rising part. But the curve not always start from 0. So this time I change this point to alpha. And this 0, there's alpha plus beta. If I change the representation to this way, then how should I modify this equation? Basically, it's just a shift. So for this case, you simply replace this original theta with theta minus alpha. Yeah, because it's just a shift in the x coordinate. And the range will also change correspondingly. So you can do the time derivative. Should be theta derivative for the velocity. So for velocity, it will just be L over beta. So that's for the rising part. How about the fallen part? So right now, let me change this one. If I set this point, so I'll do it in the same way as the previous one. This time I call this beta f. Yeah. So if my curve is like this, and right now, to make it easy, I set this point as 0, if theta equals 0. And how should I modify this equation? So if I change in this way for the fallen part, the S will become L minus it will be changed to this way. So previous for this term, there's a plus sign here, but there's no sign here, so it means it's positive. But right now, because it's a down slope, so there should be a minus sign to represent the slope for this curve. So we put a minus sign in front of this one, but because it's from a high point to the low point, so initially it's at L, so we put an L in front of it. The two equations are similar, but a bit different. Just one for fallen, one for rising. Fallen because it's fallen from a top point to the bottom point. So, but if this one is not a 0 point, then I may change. If I say it start folding at alpha f and start folding at beta f plus alpha f. How can I modify this one? So modify this equation in the same way as this one. So you simply replace, the same as this one, we replace the theta with theta minus alpha f. And you can determine the expression for this line. And so if there's a shift in the x-coordinate, you simply replace the original theta with theta minus alpha. Alpha is the angle you shift away from the origin. Any questions so far? Any questions? So for the following example, I will only show you the rising part, but you will use similar logic to find the fallen part because they are very similar. So for this uniform motion, I found it's not good because we will get infinite acceleration and also infinite jerk. So this is not good. And so we would like to use other curve to prevent this type of effect, to prevent acceleration reach infinity. So this time we use a curve instead of straight line. We use parabolic motion, parabolic curve, and instead of the straight line. So you can see it seems more smooth. Here, originally in the previous example, we just used a straight line to connect them, but right now we use a curve. So it's gradually, the slope is gradually changed. And so it seems it's more smooth. So parabolic curve, erase this first. So what's parabolic curve? Parabolic curve is a quadratic curve. Well, basically, we have theta squared. In the previous example, we only have theta. We don't have theta squared or more higher terms. Yeah, but this one, we put an extra term when compared with a uniform motion. Yeah. So right now, we put this new term, and we try to see if this one can make the motion more smooth. So right now I'm setting this one as 0 and as beta. So from 0 to beta, you will rise from, the height will change from 0 to L. So we need to find, because we need to meet this criteria first. and then we'll try to solve what's C1, C2, C1, and C0. These 2 points are like the boundary condition. We need to satisfy these 2 first. So we'll use these 2 conditions to determine the value of C2, C1, and C0. We need to satisfy these 2 displacement conditions first. One is when theta equals 0, it must be 0. That's the original requirement we need to satisfy. And the other one is when theta is beta, you need to rise to L. So we need to satisfy this one. S of 0 equals 0, S of beta equals L. So you simply apply these 2 conditions into the top equation. Then for the first equation, for the first condition, you apply 0 into this equation, so you will get C0 should equal 0. And the second one is we apply beta into this equation, so you will get C2 beta squared plus C1 beta equals L. So right now, if we only need to satisfy these 2 equations, these 2 conditions, then we know C0 is 0. And C1 and C2 can have more than one choice. You have many options to make this equation to be valid. You have one equation to define these 2 unknowns. So you have numerous solutions. But these 2 conditions are not the only 2 conditions we need to satisfy. If we go back to the previous one, in the previous example, we find a problem. We find the problem, the main problem is at this, when we take a look at the velocity sudden change. So at this point, velocity suddenly change from 0 to certain value. So if this happens, that means when we define the acceleration, at this point, the velocity change like at this moment. So the velocity is not continuous. So the discontinuous velocity will cause infinite acceleration. So we want to prevent this. We know at this point, so this one is a point. This blue point is the point the followers start to rise. Yeah. So right before this point, the velocity is 0. But right after this point, the velocity is a constant, another constant, which non-zero constant. We want to prevent this happen, because if this happens, then there will be infinite acceleration happen at this point. Any question for this one? That's what happened in the previous example. We know this one is going to happen. And if this one happens, then we'll have infinite acceleration. So how can we prevent this happen? If we want to prevent this happen, we also need to make the velocity right after this point equals 0. We want to make this point, the velocity at this point is continuous rather than discontinuous. And same as this point, we want this point for this point, because we know after this point the velocity is going to be 0. So we need to make sure right before this point the velocity is also 0. If this happens, then there won't be infinite acceleration. But right now it's not. For this uniform motion, we know because right before this point, the velocity is a non-zero constant. Any question for this one? So to make this happen, to make this v equals 0, v at this point equals 0, that means v 0. If we set this point as 0, then v0 must be 0 for this straight line, for this connecting curve. We need to make sure this v0 is 0. Then it will be continuous from the previous section. Because for the first section, velocity is 0. So we need to make sure the initial point for this connecting curve, the velocity is also 0. So we need to make this one valid to prevent a sudden jump at this point. And we also need to make this one happen at this moment, at this the top point. So this one, if we express by our certain expression, it means v beta must also be 0. So if we can make this two happen, that's what we try to do, because in the first example we know these two conditions are not going to happen, and it leads to some problem. It leads to infinite acceleration. So right now we want to make these two happen. That's why we try to use other curves instead of use uniform curve, uniform straight line. So in this parabolic motion, we want to make this happen. We want to make this v0, which means it's s prime 0, and we want to make this one also 0. And we also want to make v beta 0. Because we want to improve the motion. We want this motion to be better than the previous one. We want this parabolic motion is better than the uniform one. But if we want to satisfy these two equations, so we will do derivative for this s. So we'll get s prime is 2c2 times theta plus c1. You differentiate this one with theta, and you will get this one. And for s prime 0, you will get this expression. For s prime 0, you will substitute 0 into this equation, so you will get c1 equals 0. For the second condition, s prime beta equals 0, then you will get 2c2 beta equals 0. So that means c2 is 0. Write it. If we only need to satisfy the first two conditions, then it's fine. We can find a solution. We can find numerous solutions for C1 and C2. But right now, because we also want to satisfy these two equations, we want to make the velocity at this point is 0, velocity at this point is also 0. If we need to satisfy those these two conditions, then we'll find, well, the only possible solution is C1 is 0, C2 is 0. Then everything is 0. So we cannot do it. So it's a trivial solution. So we need to modify this one. So this curve is not a pure parabolic motion. It's not a pure parabolic curve. We need to modify this one a little bit. Yeah. Because right now, based on these four conditions, we find we cannot use a single parabolic curve to satisfy all these four conditions. These four. And if you take a look at the equations, you can find, yeah, it's obviously it's not possible because four conditions is like four equations. Each condition represents one equation. But right now, for this parabolic curve, we have only three unknowns. So we can make three unknowns to satisfy four equations. Four equations need to solve four unknowns instead of three. Right now, we have only three unknowns in these equations, but we have four conditions to satisfy. So it's not solvable. There's no solution that's gonna satisfy all the conditions. So that means we need to add one more unknowns for these equations in order to satisfy these four conditions. So what we're going to do here is we will divide this curve into two sections. The first section is from 0 to beta over 2. And the second part is from beta over 2 to beta. So we'll divide this one into two sections. The first one is from 0 to... But we'll use the same expression. Right now, theta 2, theta 1, C0. So right now, because I changed, so I'm doing this first section first. I'm doing this one first. So you still need to satisfy this one. It's starting from 0. And when theta is 0, the displacement must be 0. Second one is So I modify the condition a little bit. Right now, because it's rising, so we're taking a look of the first section. And it's still starting from 0, and so that's the first condition. And for the second condition, we need to make sure the curve rises to L over 2 at this point, at beta over 2. Theta equals beta over 2. So you need to satisfy this 2 to meet the requirement for displacement. We also need to satisfy this, the velocity at this point is 0. So you also need to satisfy this one. But for the second one, right now we actually don't need to worry about this one. We just need to make sure, so this one is the first segment of a curve. We just need to make sure for the end of the first curve will be smoothly connect to the second curve. But right now, because we don't need to define the slope for this one for now. So right now, I didn't define. This one doesn't need to be 0. Obviously, it's not 0 for now. No. So right now, I'm not defining this one. I define this 3. Because it hasn't reached the top point, which we need to ensure the velocity is 0. Right now, at this point, we don't need to ensure the velocity is 0. It can be something else. So we don't need to determine it for now. So I need to solve this one first. So for this one, these 3 conditions, you will get C0 equals 0. And C2 square plus C1 equals third one 0. Third one. So based on these 3 conditions, you will get these 3 equations. And these 3 equations to solve C0, C1, and C2. And right now, C0 is 0, C1 is 0, so you can quickly obtain C2. C2 is beta squared. So you'll get C2 is 2L over beta squared. So this is for the first segment. And you can satisfy these 3 conditions. Any question for this one? So now we need to see the other segment. Okay, let's take a break first. Okay, so let's the second part. So for a second segment, I mean this one from beta over 2 to beta. So we use another equation, although it's in the same form, but this one is a different equation because we'll have different C2, C1, and C0 for this segment. And right now this segment needs to satisfy also 3 conditions. The first one is you need to start from this the initial point for the second segment. You start at beta over 2, and the current height is L over 2. So we start from L over 2, and the endpoint you need to reach L. So that's the second condition. These 2 are for the displacement. And we also need 1 for the velocity, which is at the top point, the velocity needs to be 0 in order to be continuous with the next segment. Next segment, I mean this flat one. Because for this one, the V is 0. So you need to make sure the end point of this curve, the velocity needs to be 0. So that's why we set this condition. So right now we have 3 conditions. 3 conditions means 3 equations to solve these 3 unknowns. The C0 star, C1 star, and C2 star. So it's a bit complicated, but you can still solve it. So similar with these 3 equations to solve these 3 unknowns. And here I just show you the result for these 3 unknowns. And so, yeah, once you find these 3 unknowns, then you know the expression for the displacement. So displacement will be in this form, and so you do the derivative for theta, you will get the velocity. So we use 2 segments to form this curve. So this curve is formed by 2, because previously we used only 1 curve, 1 parabolic curve, and we find is it possible? We found it's impossible to satisfy all these 4 conditions. So right now we use 2 curves instead of 1, and to satisfy all the equations, all the conditions. All these. So mainly it's 4. Although right now we have more conditions, but the reason we are using 2 segments instead of 1 is to satisfy these 4 conditions with the yellow underline. But there's one thing we need to confirm. Previously, we haven't, when we are doing the velocity for this point, we haven't defined it. We say because right now it's not necessary to be constant. It needs to be certain value, but we need to make sure the end of the first segment, the velocity of the end of the first segment, needs to be the same as the velocity of the initial point of the second segment. So we need to check if the velocity at this point is continuous. So we need to go back to confirm if that's true. So back to the first segment, we know the velocity. So velocity, you do the differentiation of this one with respect of theta. You get this velocity, and the velocity at the end point of the first segment, you just substitute beta over 2 into this expression, and you will get the velocity is 2L over beta. It's 2L over beta. That's for the end of the first segment. It's the end of the first. But right now we also need to find the initial point for the second. for the second segment. So I also do a differentiation for this displacement equation and to find the velocity expression. So I get this velocity expression. I also substitute the theta with beta over 2 because it starts at beta over 2. Beta over 2 is the initial point. So you substitute beta over 2 into this equation and to find the velocity. You'll find the velocity is also 2L over beta. So this is good because that means the end of first one and is the same as the initial of the second one. So that means their velocity is continuous. They are the same. There is no discontinuity between these two segments. So by using a parabolic motion or parabolic curve, we divide it into two segments. So there are two parabolic curves in this curve. Two curves in one single curve. We found that you can satisfy these four conditions. It's the displacement, of course, you need to satisfy the displacement, but I can also satisfy the velocity. So the velocity of the initial point is 0. So this property can make the velocity at this point is continuous. And also this point we found is continuous. So that's a good thing. It's better than the previous one. At least right now the velocity is continuous. So once we get the displacement, we do a time derivative to get a velocity. So right now I get velocity is in this form. Velocity is going to be a constant for each segment. If you take a look at this one, it's basically a constant times theta. So it's a slope. It's a straight line for the velocity. So the first one is going up, the second one is going down because the second one is negative. The negative sign before the theta. So we can further find the acceleration. Acceleration is to a time derivative or theta derivative for this curve. Then you'll find the A is in this form. So you find any problem with the acceleration? Although right now we don't have infinite acceleration, you can see the acceleration is continuous at those points. At this point, it suddenly change from 0 to a certain value. And at this point, because in velocity there's a sharp angle here, that means it suddenly change from certain value to another value. So you can find in acceleration, there are many sudden jump at many different locations. So once you see this, you can probably imagine we will get infinite jerk for this motion. Because the sudden jump, that means when you do a differentiation, this point is not continuous. So you will get a finite value for the differentiation. So parabolic motion, well, is better than the previous one. At least right now we don't get an infinite acceleration, but we still get infinite jerk. So it's better, but it's still not the best because still the discontinuous acceleration leads to the infinite jerk. Any question for this one? So we probably need other curves to do the job, to connect these 2 points. So right now you probably see a problem. Right now we only satisfy 4 conditions. 2 is for displacement, and 2 is for the velocities. For this one, this parabolic, for the uniform curve, the one in the previous slides, we only satisfy these 2 equations. And for the parabolic motion, we satisfy another 2. But right now, you can see if we only satisfy these 4 conditions, it's not enough. Because you're still getting finite jerk. To prevent infinite jerk, then what condition do we also need to satisfy? Acceleration, right? We also need to satisfy the acceleration, so we also need to make these 2 happen. Right now, these 2 are not happening because we don't have enough variable to make these 2 happen. But if we can make these 2 happen, that's because for this flat region, S0, V0, A0, J0. So to make this new curve, this continuous, we also need to make the initial value, initial displacement, velocity, acceleration, also be 0. We need to make them continuous from this very first segment to our rising segment. And for this parabolic, we only satisfy these 4. We hope we can also satisfy the other 2. So we'll try another curve and to see if it can work better. So another motion we are introducing here is called harmonic motion. Harmonic basically means sine or cosine. So use this type of function, and to see if it can satisfy these 6 conditions. If these 6 conditions cannot be satisfied, then we know there won't be infinite jerk. So for harmonic motion, we'll write the equation first. So here's a general form for harmonic motion. So basically put a constant and it's plus another constant times cosine and constant times theta. And we'll see if this one can satisfy these 6 conditions. Right now it seems impossible because we have only 3 variables, but we need to satisfy these 6 conditions. 6 conditions means 6 equations. 6 equations should solve 6 unknowns instead of 3. But let's see how much this can do. Because it's sine cosine function, it's harmonic function. So it may work differently from the quadratic equations. So let's see. So let's just apply those conditions one by one. The first two, we must satisfy the first two because we need to connect these 2 points with a curve. So these two displacement must be satisfied first. Then we'll go with the velocity. If this one can be satisfied, then we'll go with the acceleration. Okay, so let's take a look of the first 4 conditions. We still need to take a look. We take a look on the first 4 first, and to see if this 4 can be satisfied, then we'll go further to see the acceleration. So there's a general form of harmonic motion, and you do the differentiation over theta, you get this one, and you do it again, you will get the acceleration, and you set this form. So you need to satisfy the first 2 equations first. So you just substitute this beta equals 0, and S must also equal 0. So you get this first equation. So for second condition, you get a second equation. So for the first equation, you get CO or C0 plus C1 equals 0. For second one, you get C0 minus C1 equals L. So based on these two equations, you can determine C0 is A over 2, C1 is minus A over 2. So we already found C0 and C1. And so let's take a look at the velocity. So for velocity, we need to make sure both the initial point and the end point, they must equal 0. So for the first one, you will get this equation, minus C1, C2 sine C2 times 0 equals 0. And actually for this equation, no matter what value you apply for C1 and C2, it's always 0 because sine 0 is always 0. So we got this equation, this condition satisfies. It's not because we are tuning the C1 and C2. It's because it's a sine. Use sine, and initially it's 0, so sine 0 is always 0. So it's kind of, we got lucky for this one. We don't use any unknown in order to satisfy this equation. And for the second one, you substitute theta equals beta in this equation, so you get minus C1, C2 sine C2 times beta equals 0. So to make this 0, well, you can either make C1 or C2 0, but that's not good because there's a trivial solution. So you want to make a more general solution, which is if you make C2 equals beta over pi over beta, then this sign will always be sine pi. Sine pi is always 0. Of course, what I say is, of course you can also make C1 equals 0 or C2 equals 0 to satisfy this equation, but this is not a good choice because there's a trivial solution. You'll make the whole term become 0. And we already solved C1, so C1 can be 0. So to satisfy this one, you can determine C2 equals pi over beta. So right now, we've used all three unknowns. But right now, these three unknowns can satisfy these four conditions. Can satisfy the displacement and velocity. But we have no more unknowns for acceleration. So we'll see if this one, even we don't know the, just finish this first. C0. So based on these four conditions, we can determine the S is in this form. So we now need to check if the acceleration is satisfied. Maybe we got lucky, maybe they're just satisfied. So for S double prime, we will get constant C1. So for the acceleration, we can find an expression in this form. And so what's the value for S double prime of 0? It's not going to be 0 because it's cosine 0. Cosine 0 is 1, so this one is not 0. Beta. Still not 0. So it means with this one harmonic motion, we still cannot satisfy these two conditions. So it's similar to the previous one, we still get infinite jerk. So the condition right now is similar to the parabolic motion. Still get infinite jerk. And right now all of the unknowns, so we have no more unknown to satisfy these two conditions. Any question for this one? So we'll continue to explore if there's any options we can use as the curve to connect these 2 points. Maybe we can find another curve to connect these 2 points, and that can satisfy all these conditions to make a jerk not infinite. So here we are going to introduce another type of curve. It's called cycloidal curve. Here's displacement, so we call it cycloidal displacement. And cycloidal curve is determined in this way. So suppose we have a small wheel here, the small wheel with a radius of r. Is the angle of the small wheel is 0.5. And still the x-coordinate is the theta. So similar to what we've done for the displacement. The x-coordinate is theta, the y-coordinate is the displacement. And right now we are using this small wheel to generate the curve. And how we are going to do it is we will roll this small circle along this line, and we will project the dot here. So we set a dot on this circle, and a dot here, and then I'll have another dot here. So I'll start to roll this circle, and to roll from this point until this point. It's doing pure rolling motion. So every time I turn a certain angle, so right now in this coordinate, in this x-coordinate, there are 2 things. One is the theta. The theta is the original theta. Displacement is the original displacement. But right now I'm setting another coordinate phi here. So it means from this point, this small circle is going to run 1 cycle. So let's see the finish point. So you'll run 1 cycle. So I'll roll this one from this point to the top point, and once you reach this point, you rotate 360 degrees. So we call this a complete cycle for a cycloidal motion. So back to this one. What I'm going to do is when I rotate this one, so I also divide this one by 360 degrees for this circle. Because you rotate by 360 degrees, you rotate for 1 cycle. So I count from this point to this point. Right now I divide, in this graph I divide into 6 segments. So each segment means 60 degrees. And 60 degrees. So each time I'll divide it, I will roll it by 60 degrees and to project. So anyway, I'll start to roll this one. And I will project this point on the corresponding vertical line. I just vertical line. So let's take a look of second one. So for second one, I rotate this small circle by 60 degrees. So it's rolling by 60 degrees. So right now you reach this point. And right now I'm projecting this point, the point I'm going to project on this line. I project this point on this, this vertical line. So I rotate by 60 degrees. And right now, this one also, if you take a look of the coordinate for phi, is 60, 120, 180, etc. So right now I rotate it by 60 degrees, and I project this point to this vertical line. So this point is gonna be going to represent the cycloidal curve. And then I keep rotating another 60 degrees. So right now I also project this point to this vertical line. Right now it rotates by 120 degrees, so this coordinate here is 120. So I project this point to this vertical line. I keep rotating, so right now I rotate by 180 degrees. I project this point to this line. So I keep doing this, and I roll by 60 degrees. I project this dot to this another grid. And this one project here. And finally, the top point, this small circle runs for one cycle. So there's a complete cycloidal motion, cycloidal curve. So cycloidal curve is generated this way. You will need to set a small wheel and to project a dot on the wheel to certain coordinate. So that's how we generate cycloidal curve. And right now, well, we generated, so we need to find certain expression. We need to write this curve in a form, in a mathematical form. So right now I'm trying to express this motion or this displacement in an equation. So how can I do it? So there are some parameters here. One important parameter is the radius of the small circle. So let's back to the first one. Right now, if I want to determine, here is this. This is the S, the displacement for the cycloidal curve. This point or the other point, this one is the mu S. So I'm going to express this S in the equation. Then how can I determine the S? If I know the R, I know the phi, how can I determine the S? It's actually not difficult. So right now I'm using the coordinate of this small circle instead of our original coordinate to determine S. This S, this point, is basically this one minus this one. So what's the value of this one? Because it's doing pure rolling, so the length of this one is the same, the length of this arc. the length of this one is the same as the length of this arc, because it's doing pure rolling motion. And how about this one? It's another arrow, another dimension. This one, R sine phi. The length of this part is R. R is the radius of this small circle, and times sine phi. So I can express this displacement, my projected point, as by using R phi minus R sine phi. But because our original coordinate is theta, right now we're using phi, but because we generate phi for this small circle. But initially we should determine this one in our original coordinate, in which the angle is theta, not phi. So we need to convert it back to phi and beta. So how can I do this? And also the height. Right now, when this small circle, run for one cycle, it will move by 2 pi r, right? But our original coordinate, we use L instead of this 2 pi r. So we also need to convert the displacement from this function of r into our original expression. Any question for this one? So we need to change r and phi into our original coordinate. Original, we use beta and L. So we somehow need to convert, we use beta, L, and theta. We need to convert it back to our original coordinate. So right now for this one, to convert, to make a conversion between L and R, you simply, because for this one, this small circle, you run for one cycle. One cycle you run for 2 pi r. And this 2 pi r must be the same as L. Because the length for this circle to run is L. So 2 pi r equals L. You can replace this r by the expression of L. So you'll replace the r with r equals L over 2 pi. And on the other hand, we also need to convert the angle. Original, for the coordinate of a small circle, you run for 2 pi. You run for one cycle from this point to this point. And each time you rotate with certain angle phi. So phi over 2 pi should be in the same ratio as theta over beta. Theta and beta is our original coordinate. For this one, we want theta from 0 to beta. And for the small circle, we run from phi equals 0 to 2 pi. So phi over 2 pi is the same as theta over beta. So you can also use this expression to determine or to convert phi into theta. So by doing so, you can convert this displacement into the form that's in our original coordinate. And yeah, the last one is just a rearrangement of the second equation. So again, we need to make sure if this one can satisfy these 6 equations. And let's see if this one, this complicated curve, can do this job. And we initially determine the displacement. So anyway, we already find, there's no unknown here. Everything is known. That's because we already determined the displacement when we are drawing this product. So right now there's no unknown. So this one is our final curve. There's no parameters we need to determine. And we'll just see if we can satisfy those conditions. Once we get the displacement, you can do a differentiation over theta. You get a velocity, and do it again, you get an acceleration. So right now we need to check if we can satisfy all these 6 conditions. And the first one, we still check with the displacement. And yeah, if you substitute theta with 0, this term will be 0, and this sine 0 will also be 0. So you will get S beta equals L. And if you substitute, if you substitute theta with 0, yeah, you will get 0. If you substitute theta with beta, this one will be 1, and this term will still be 0, because it will just be sine 2 pi. sine 2 pi is 0. So the second term is 0. So you'll get S of beta equals M. For the velocity, then we can also just substitute theta with 0. And cosine 0 is 1. So 1 minus 1, you'll get 0. So S prime of 0, you'll get 0. How about S prime of beta? If you substitute beta into this equation, cosine 2 pi is 1. So 1 minus 1, you still get S prime of beta equals 0. So last one, the acceleration, you substitute theta equals 0, sine 0 is 0. So you get S double prime of 0 is 0. Another one, you substitute theta with beta, you also get sine 2 pi. Sine 2 pi is 0, so you also get 0. So by far, this one is the best because it satisfies all the 6 conditions. We finally found a curve that can satisfy all these 6 conditions. So we have one last. So you can take a look of a curve. They don't go infinity. They don't go infinity, even with the jerk. So next time we'll talk about the polynomial motion, and we'll also see if this one can satisfy all these 6 conditions. Okay, any questions? So anyway, so that's it. So I'll see you next week.